Hello, everyone. In this section, we're going to discuss training models. Specifically, we want to look at gradient descent methodology. In linear regression, we use normal equations to solve data. And you could also leverage SVD, single value decomposition, to estimate theta as well. And then here we're taking a different fresh perspective, which is from gradient descent perspective. What is gradient descent? Gradient descent is a generic optimization algorithm capable of finding optimal solutions to a wide range of problems. So in this graph, you can see x-axis is a theta, y-axis is a cost. So we're hoping that we are able to find a theta estimate that is able to minimize the cost. And then for gradient descent, there will be two parameters that you need to consider. One of them is random initial value. Second is learning step. So as you move towards the minimum value, you probably want to also to consider to adjust your learning step size so you're able to achieve that minimum. So this is a graphical explanation of gradient descent. So the learning rate is important. If the learning rate is too small, as you can see on the left chart, what happens is you continue to move small step size, continue to update your theta, but it takes forever to find the theta estimate that would be able to minimize that cost function. On the other end, if the learning rate is too large, so what happens is you start here, because the learning rate is too large, you goes to a new new solution of the theta, and as you continue to update, you jump back and forth and not able to find the minimum, the theta that would give you the minimum cost. So you have to be really careful about the learning rate selection in gradient descent methodology. There are also some pitfalls for gradient descent. One of them could be, you can see this graph is going to have one local minimum and one global minimum. And unfortunately, if you selected the initial and the learning rate differently, you could end up being the local minimum. You're just not able to jump over this hump, not able to come back with a global minimum solution. That's one potential problem. The other potential problem could be as you continue to update your solution, and then just because it's plateaued somehow for the cost, so that you're not able to continue to update your theta, the algorithm thinks that you already found the minimum solution. In that case, it's another potential issue that you want to pay attention to. One important aspect that we want to mention is scaling made gradient descent easy. So on the left-hand side, you have theta 1 and theta 2. In this case, you saw that these are the cost function contours of the cost function. The darker the graph, the higher the cost function. So the lighter the graph would be the minimum cost area. So if you are able to scale your features to normalize the features, then it's easier for you to find the solution. So you would be able to figure out where is the right direction to move to and find the minimum rather easily. On the other end, if your theta 1 and theta 2 are not scaled, then what happens is it may go back and forth and trying to figure out the solution of the minimum. Just give you some graphical illustration and understanding of how the scaling can help you. Let's look at batch gradient descent. We want to calculate partial derivative. It's like asking this question: what is the slope of the mountain under my feet if I face east? And then asking the same question facing north, and so on and so forth for other dimensions. If you can imagine a universe with more than 3 dimensions, then you will be able to figure out the partial order derivative of all the dimensions. And then for MSE, partial derivative in terms of specific theta can be calculated by this way. And then this is also can be in a vector form for each one of them. Putting them together would be in vectorized solution would be 2 over m times x transpose x theta minus y. This is batch gradient descent. Once you are able to calculate all of them for each single theta zero at specific point, you would be able to make a decision on where to move in terms of your next direction. So this is a gradient vector. So what you do is in each step, what you do is start with your previous step of theta and moving towards the direction that you figured out based on your gradient vector, and then minus a learning rate eta times this gradient vector. So just continue to update your theta for the next step, calculate the gradient vector again, and then update the theta, keep going until you think the algorithm actually converges. In Python specifically, what you can do is just do what we just said. You could update this. So let's look at here what you would be doing. For n iterations, each time you calculate your gradients based on the function that we just saw, and then you update your theta based on theta minus eta times the gradients. And then by doing this, you are able to come back with your theta estimate, which is the same solution as using normal equations, because we know normal equations are closed form solution. Good news is by using gradient descent, you don't need to deal with the matrix inverse. There's a chance that the matrix cannot be inversed, right? So gradient descent is really looking at getting to the theta estimate from a different angle than SVD algorithm. That's a batch gradient descent in Python. So here we want to illustrate that the learning rate could be an important factor, as we saw earlier. It could be too slow or could be jumping around and cannot find the minimum solution. So when eta is only 0.02, trying to approach, but it's just updating and takes a while. Even for 10 iterations, it's still cannot find the right solution. And when eta is too big, 2.5, it just jump around and not able to be close to the optimal solution. When eta is 0.1, within like 5 steps, it's already very close to the final optimal solution of the theta estimate. Let's look at another variant of gradient descent. It's called stochastic gradient descent. Stochastic gradient descent picks a random instance in the training set as every step and computes the gradients based only on a single instance. So that actually makes a big difference, because earlier we said a batch the whole data. But now we're talking about only one single instance to calculate the gradient. Apparently, it will be much faster because you don't use the full data set to calculate the gradient. You only use one instance. However, it actually comes with a cost because it just converges a little bit slower. It would jump around, and finally trying to figure out this minimum cost point, it just takes longer to converge. And in here you can see that we just randomly pick one instance of xi and one instance of yi to calculate the gradients and get eta and update your theta. For the gradient descent, we got 4.215 and 2.77 being our theta estimate. And using stochastic gradient descent, we got 4.210 and 2.748, which are very close to the closed form solution. So this is a second line implementation of stochastic gradient descent. So what you do is you just use SGD regressor to fit to, once you do that fit, you're able to figure out the intercept and the coefficient. Again, it's very close, even though it's not 100% identical, but it's very close. Here, just want to introduce one more thing that's called mini batch gradient descent, which is which is in between of batch and stochastic. In stochastic case, it jumps around all the time, which is a red line, jumps around and finally settled in a solution. The solution is theta 0 is 4.2 something and theta 1 is 2.77. And then the batch is more straightforward, right? It just goes to the solution rather quickly. However, mini batch is somewhere in between. It actually takes a batch to calculate that gradients instead of one instance or the full data set. It's only a mini batch. In that case, it lives in between of those two types of solutions. It jumps slightly, but it converges faster than the stochastic gradient descent. This is a comparison of so far what we learned for linear regression. So we studied normal equation, SVD, batch gradient descent, stochastic gradient descent, mini batch gradient descent. And then good news is, you need to figure out whether you need to do some scaling and how you can leverage what you have in terms of the regression methods, and then in terms of its speed, they also have different performance. Okay, I'll stop here for linear regression in general, which including normal equations, SVD, and gradient descent.